Well then, we start from changing some notations that were introduced in the last lecture and some concepts. In fact, changing them from quite standard ones to a bit non-standard. So, renotating and perhaps better redefining the products and co-products. First, some generalities, and sorry for the possible repetitions. One of the strong advantages of categorical language compared to the traditional set-theoretical language is its non-linearity, the possibility to switch on our geometric imagination on the level of mathematical language itself. Mathematical language is generally non-linear. Everybody who tried to express some mathematical idea in electronic letter knows very well that there are troubles representing the fractions. Well, you can write, of course, 1/3, but it is worse. Well, integrals and matrices and so on. A more traditional part of mathematical language is geometry with its sketches. But as for the categorical language, it is non-linear and geometric in its essence and its nature. So maybe you noticed that during the last lecture I felt some unconformability. I was not complete conformal, just drawing what I'll repeat now, say the project of xn n running over some small discrete category, because they were we needed lots of arrows, the traditional arrows like I'm writing now in a random way, and it's not a good this notation is not good, as you feel perhaps. There are no n primes and double primes and so on, but I had to express somehow that the arrows go from the product to all the multiples of it. During this week I have understood that the general idea, now let's fix our notation again, n is being a small, it is category by that can be seen by the font is a small and discrete. Category C is an arbitrary category, and we have a small functor to which we give no name, but it associates to an object n, an object x sub n. So the wrong idea, and quite traditional idea, that in some cases, I didn't emphasize it enough perhaps, in some cases the product like this, I'll erase this memory of the previous lecture, the product is thought of being an object of the category C. Now I want to refuse to leave this idea and substitute by a more geometric one. To do this, I introduce the concept of star of the discrete category n, and the simplest thing to do is just to draw it. This is what it is. Sorry, I wanted to mention, perhaps without any notation, I just write down that here are the objects n's from n. It was just mentioned that there are three close concepts like small categories, directed graphs, and diagrams. I hope it is intuitively clear that these things are more or less the same, and let's just use this understanding to define the product in a better way. So here is the star of n, yet not completely defined, but as for the word star itself, it is taken from the theory of graphs. This is one of the simplest kinds of graphs. What is important from the nonlinear point of view is that we think about it as about simplest plane tree, this time directed tree. So this is why the vertex, I want to use the large star for its central object, and this is the picture we generally understand and keep in mind. And what is new in today's interpretation of products in any category is just using this planar intuition in constructing the corresponding diagram. So this is not a nice notation. Now let's define the star of n formally, and n is a small category, that is a set. It is a set, and we can add to it one element set, and perhaps draw it like this. Now something new is going to happen. We draw our category N here as a circle, just meaning that it's not a good idea, because there is no geometric connections between the objects. We just think about it, about the objects of this category just lying in the circle. As you see, I am not trained to draw it because the interpretation is quite new for me. However, suppose this is an N and we add the additional object to the center. Just to the, there were no more morphisms at all. Instead, besides the usual identity arrows from any object to themselves, there were no other morphisms, and now there is a set, and the morphisms in this new category star over N, the only morphisms that star of N, and the only morphisms that occur now are the morphisms from the central object to N, and all these morphisms are, again, sorry for the ability, the ample stars of different kind in notations and in the language, but it is so. We have no other notation for a one element set. So this is what is drawn in this new category star of N. We add an arrow from the center to every object of our discrete category. Now, what about the product? I want to declare that the product of this kind, when it exists, is nothing but, belongs to, not to C, as we have thought previously, and as everybody think, but let it belong to C, to the power star of N. Let me remind you that it means the functors, the category of functors from a small category star of N to C. That just means that every object of this category is supplied as we know perfectly from the standard definition of the product, by the arrows that are just projections. Projections, maybe I write it like this. These arrows like this are what is standardly denoted by projections of the product to the factors, the projections. And now the universal property of projection that I'm not going to repeat formally, but I want to formulate it pictorially using the geometry of cone. That means that as soon as we have a system of morphisms of any object z to the objects of n, that means as soon as we specify an object of our initial category together with the morphism from z to it, that should be consistent, but there are no additional demands for the consistency, since there are no non-trivial arrows in the category n. And then we demand that there exists and is unique such an object about which we can now think as about the axis of a cone. So nothing really new has been said now, but the new picture occurred, and maybe the new and better understanding of where the products live. Maybe we meet a small inconvenience here, because the usual understanding is that the object itself lives in the basic category C, but it is supplied by a set of arrows to the factors. Thinking in these terms, we just put the product into a larger category, and the standard concept can be restored by applying the forgetting functor. But I think the main advantage of what is suggested now is in some clear geometric picture that you see, and I suggest that you get used to it. Well, so as for now, any questions about this construction, please? I don't know why I still didn't hear a voice over any distant participant. Can anybody please say something so that I could be sure that you can participate in voices? Oh yes, somebody, perhaps it was Anton, somebody said something. Thank you. Well, so I leave it to the participants to draw the object and think about co-products. I just perhaps mention so left to the, how do I call it, listeners, how do we call you? Everybody used to say left to the reader, but you don't, up to now you don't read anything. I'm just in preparation and process of preparation the material. But there are lots of obvious constructions of products. I would like to mention one non-trivial and very important example of product, of co-product, so that you could draw something and think in geometrical terms. So in the category of groups, the coproduct is nothing but the free product. Sorry for one more star. It happens so that today's lecture is just full of stars. And an example that again I advise strongly to think about is that the free product of two simplest cyclic groups of order 2 and order 3 is just the classical group PSA2, the modular group, very important in lots of mathematical theories. So you can, just to train these pictures with examples, you can consider this case. Okay, so that was about that part. If there are no questions, I erase everything.
I have one question.
Oh yes, please.
How we understand universal property in this new definition? How we redefine our universal property?
So yes, it should. Thank you. It should be pronounced in words in a rather long manner. As soon as we have an arbitrary object, it could be maybe marked here, an arbitrary object of our category, together with a set of arrows directed to all the factors. Then there exists and is unique this broken, thick broken arrow to the center. And here we have the consistency conditions, because there are lots of triangles and all of them are commutative.
But now we assume product is an object from different categories. Yes? So our product is not in, we mean it's in our C, or?
Sorry. Our product is here. It is it lives in I perhaps I better repeat what is living here. It is a small functor from the category star of n. That means the object here, together with all the arrows to the objects marked by the small category n.
So we should have a morphism from C. So for every Z in C, we have a morphism from, or
Sorry, and thank you for your correction. Of course, we have not just an object Z. Of course, Z lives in C to the nth. Z comes together with all its arrows, and it's a very important correction. Thank you.
Можете просто сказать, что было проделано, не пояснить, а просто сказать, что вот было проделано до этого.
Что было проделано?
Что было проделано? Можете просто сказать, извините, немножко пришел позже, что было проделано.
It is just a modification, redefining, modification of product, of the definition of a product, of the standard definition, but now we introduce the category operation, star of discrete category, that is just adding the thinking, the important imaginary part of it is thinking about discrete category, objects of discrete category. living in the circle and the additional object in the center of it. Well, identifying still, I was just in the process of erasing it. The idea is just to use actively the Grothendik's idea, and I'm sure the way he thought about certain objects of strong using the usage of the category of diagrams. This is just the first modification in the Grothendik style. So to an arbitrary discrete category, we associate a simple category of diagrams like this. These are the diagrams, for the time being calling them stars. Of course, my suggestion is to introduce cos star here in an obvious way, just changing the direction of the arrows, and just modify the definition of the standard definition of the program, the product. What we gained is well, the new understanding of where the product lives. In the usual language, it lives in the same category, but is supplied with lots of arrows. Here we just put it into the definition and try to draw it like this in the base of the cone. But the whole, what is really important is to imagine the product with the to relate the idea of the product with the geometry of cone. Okay. Are you satisfied?
Yes, yes.
Mm-hmm. Good. So now I complete the erasing part and return to the point of the previous lecture where we have stopped. Again, I need some small notational corrections. So these are the it was discussing the equivalences of several kinds in categories. Well, I will not repeat the discussion of the isomorphisms of objects instead of the equality in the sets that is used for the identification of objects of a fixed category, but the basic concept is the equivalence of categories based on the concept of natural transformations. And here we stopped, and by some technical notational detail, I want to reproduce the notation for the natural transformation. Natural transformation of functors. And repeat again that you better think about it in the terms similar to homotopic equivalence in topology. So over to suppose we are given two categories and two functions. Then a natural transformation that is usually denoted somehow, but I don't want to do it. We have enough letters here. So the transformation itself is the association to every object of the category C, the two objects denoted exactly like we do it in the sets, and G of X are the objects of the category D. So we discuss the transfer, it is just the given data. But then given, then we transform the arrows as well, and given any two objects of the category C and any, here we can use just the usual quantifier because alpha, well, let's write it completely, alpha lives in the set of arrows from X to Y. And then we have a square. So there was a small misunderstanding a week ago, just because I did not introduce and assumed it as known, the notation for the action of morphism of the functor on the morphism. Let me remind you that we consider only the covariant functors, otherwise we use the word cofunctors and the inverse categories. So all the functors are covariant, and we denote it like this. Maybe I'd better write here as we should write and think. By the way, here again I use the non-linear language. So, and perhaps I better write it here for f of x and f of y. Our functor is what you see, and I prefer square brackets just to use our set the usual notation Cf of alpha of x. For in the category of set, the functors are just mappings. So that's why we use the, I prefer to use square brackets. It is also not quite traditional. And usually, in order to make notations lighter, we use the notations f of alpha, like alpha star, meaning that the f of this alpha lower star is clear from the context. However, here, if these data are given, we have an obvious square. Let's write it down. So there are f of x. Sorry, I'm not sure that I'm drawing this square in the same, always in the same direction, and f of y and g of y. Yes, so we have the objects of the category D in the vertices of this square. Now what do we have? The vertical arrows are f. In the previous lecture I just denoted first them both by alpha lower star. Well, one of them with the help of somebody, but of course in this context it would be clearer if we use a bit more detailed notation like I'm using now. And well, this transformation has no names. We do not denote it somehow. It is the transformation of the functor we are defining. So it is demanded that all such squares are commutative. So this is a small variation and repeating of the transformation of the concept of transformation of functors. By the way, sorry, I don't remember whether I quoted it a week ago, but MacLean, the author of the whole concept theory, is told to say that he had introduced the whole category theory, not for the objects, not for the categories, not for the functors, but for the transformation of functors. And I don't go into details now by the following reason. The first application of these ideas belonged to topology, and more than that, to different homological theories that were developed with the active participation of MacLean, and we are going to discuss the corresponding cohomology theories in frames of our course. So then, well, you repeat, you can follow any source or suggest yourself the remaining parts of the definition to finally to describe the natural equivalence of categories. Well, first I need to erase almost everything here. Any questions about what is said and written on the blackboard now? Okay, so we leave it and discuss a sometimes subtle point, the difference between the concept of being isomorphic. Perhaps I leave this as a step already made, and the next subtitle is the one we have just dropped at the end of the previous lecture. So the difference between being just isomorphic and canonically isomorphic. So these categoric analog of relation between objects of the categories mean that these characters are put between the objects of the same category, and some of them are legal, are correct, some are no, but we should distinguish them, and we just stopped at the suggestion to discuss it using the standard example. Here our category, well, for some time I will repeat the notation that K is some for which we happily have the special character, is some fixed field, and for C we we consider the category for which there was not yet special notation, but everybody knows what it is. So this is the category of vector spaces over K, and we consider some of the statements I'm going to make are valid in the category of all vector spaces, but the main example considers only the finite dimensional. So this is our central category, and now again I think the ninth star of today's lecture is the star of, well, it is said, defined in words as a conjugation, or taking the dual space. Now what it is a co-functor, as we know, denoting it like this, and to a space V, as everybody knows, we associate the set of linear mappings from V to the ground field. That is the definition of this notation is not good at all. Well, let me underline it somehow and just avoid mentioning the some forgetting factor. It is, we mean here the set of linear functionals, denoted in a standard way like this. So it's the set of linear operators or morphisms from V to the one-dimensional space over K. Anyhow, everybody knows what it is. Now, why is it a functor? It is because as soon as we have two objects, two vector spaces, and a morphism, here we better write like this, a morphism alpha, it then here we use the upper star that maps the duals in the inverse direction. Just introduce one more notation of the application of the functional to the vector. That means that, say, the functional star. Maybe let's write it down. Here what we have said theoretically is alpha here, W here, K here, and K here, and well, psi here from the end of the Greek alphabet, or the, well, some piece of Greek alphabet. And here is the alpha upper star of psi. That works in the only possible way, associates psi from here. It associates to functional on the W, the functional like the only one that can be thought of. Well, I think we better there is just one K. Let's use the diagram like this. So here we put the value of the functional psi on where can it be applied only to alpha over V, and here is the well-known definition of the conjugate linear operator. In some institutions, well, maybe I can say technical, there is tradition to define the linear operators in bases and in terms of matrices, and in this case it is very important to realize, to introduce the concept of dual bases to a given one, and to realize the upper star as the procedure of transposition of the corresponding matrix. So, so now we, well, let's just fix first that V, any V, is isomorphic to V star, but not canonically. It is a bit difficult to give a precise sense to it, because you could well, suspect that there exists some canonical equivalence, but we are just not aware about it. It is not so. If this equivalence existed, it would respect some automorphisms that it does not. I just give an obvious comment that if such an isomorphism is arbitrarily fixed, sorry, here is the point where we use the finite dimension, the fact that they are both finite dimensional. It is, for example, using dual bases, it is easy to see that the dimensions of these spaces are the same, therefore they are isomorphic. But as soon as such isomorphism is fixed, the canonical quadratic form occurs that maps V and V prime. For example, it could be symmetric, it could be skew-symmetric or whatsoever, but say we can apply this I over V to V prime, And this is an arbitrary bilinear structure, or if you like, an arbitrary quadratic form on the vector space. So this is an informal explanation why these are non-canonically isomorphic. However, if we iterate this procedure, perhaps I have a nice place here. If we iterate it, then we have alpha double star v 2 v double star, and you check then that the double application of this defines the canonical equivalence. I won't write down the details and think it is quite useful for the people who want to work in the category language actively once in your life, to check all the details with all the notations, and to see that here is the natural transformation of the category of vector spaces to itself. The arrows are turned again, so it is a functor, and it is naturally equivalent to the identity functor. That means exactly that we have a right to write down this character, and informally this means that this functor double star identifies not only the objects but all the arrows in the consistent way. This short sentence contains a lot of standard simple facts that have to be checked once in the life of any modern mathematician. Any questions about this? Now, then I erase it and discuss another example that is as standard as this one, but maybe not so often discussed in the literature. So this is the Pantryagin. Another example is the example of Pantryagin. Pantryagin duality. Well, at this point, anybody can be puzzled and ask whether we are going to discuss everything in this course. And I should admit that the relation of Pantryagin duality to the Grotendika topology is somewhat hidden. However, if we are going to consider seriously the existing cohomology theories, we should take it into account. Though now I'm going to mention it just as an example of duality and the difference between being isomorphic or non-isomorphic and canonically isomorphic. So here our central category is the category that I can describe only in words, because it's perhaps the first time when we merge two kinds of structures. So it is the category of locally compact Well, in the standard category theory, it means that whenever I'm using an adjective that makes sense being applied to topological spaces, I mean that there exists a forgetting functor from what I'm going to write down to the category of topological spaces. Local compact abelian groups. And the other part says that there is another forgetting functor. Forget the topology and keep the group structure. That needs no comments. Well, perhaps I put the double braces. As usually, we define the class of objects and assume that the morphisms are the just the set theoretically morphisms that are mappings that respect both structure. That means that they are morphisms of groups, continuous morphisms of groups. Now, in this category, there is an example that is not quite clear immediately to be an outstanding one, and the notation is again not quite standard. It is just a circle. I prefer to write it down, to think about it in the complex plane and to denote it in some different way than just a circle. And of course we mean that it inherits the multiplication from the field of complex numbers. And then the Pentragian duality is similar to taking the conjugate linear spaces, and well, it is taking the group of characters for which we do not introduce any notation, but here to an object J, Pentragian is associated. We'll denote it like this in a similar way to the dual vector space G check. Sometimes the hat is used, but then well, some clinch of annotations happen. That is just the set of morphisms in this category from J to C1 to the circle. So this is a co-functor. Unlike the category of the case of category of vector spaces, the groups are usually locally compact. Abelian groups usually are not isomorphic to their duals. Well, it is called the Pentragian dual. And the basic examples are the Z check is defined by the image of the generator of Z, and it can be sent to any point of our C1. So this is C sub 1, well, can I put the equality sign? No, just, well, the most accurate way would be to say that it is isomorphic. On the contrary, C1 check. What are the morphisms of the circle to itself? Just raising to any power, any integer power. So it is the check, and considering the this is one of the illustrations that the GW dual is canonically equivalent to the original G, and again you're suggested to check it directly. And well, this is the illustration, and in the same time, if we turn from the groups to the sets, to the spaces of functions on them, since they are locally compact, we better consider not all the functions, but develop some measure theory and consider some functions that are good enough. Then this isomorphism can be given an interpretation of theory of Fourier series. Basically, a function on a circle is a periodic function on the real line, and the Pontryagin dual associates to it the set of its the coefficients of its Fourier series, and then R is kind of self-dual. Here it is very important. I don't know whether I have some other chalk just to suggest your thinking why we cannot put the canonical equivalence here. So it is the additive group of real numbers, where here I always mean additive groups of Z and of R. So they are isomorphic but not canonically, and this is the reason why it is the theory of this isomorphism is the theory of Fourier integrals. As you know, in the Fourier transformations, various authors put some coefficients like square root of say 1 over square root of 2 pi, or do not put them. Then the inversion formula. Well, the inversion formula for the Fourier transformation is exactly the self-duality of the second is the fact that taking Pontryagin dual is the anti-equivalence of the categories. So, I don't know, there is one of the participants, Pasham, well, one of the participants told me that the real mathematics is algebra, and the Pasha Martiniuk And well, the mathematical analysis is well some obsolete nonsense. I think this example deserves attention, at least to illustrate the fact that categorical language and categorical concepts give a very concise formulations for the classical facts in different domains of mathematics, including classical analysis. Any questions about these concepts? So I didn't say anything in general, and I think, and we better move further now. But I think that as soon as you think over these examples in all the details, you understand the main constructions for the general case. Now, what we discuss next, maybe with some, maybe the plan of today's lecture can seem to consist of some arbitrary jumpings, but in effect, this and the next topic are, I hope, are going to be related to the main objects of the course. So it's time to start discussing representable functors, or better, now let me think. There is an option, representable functions, or perhaps representability, because lots of functors are not obviously representable or non-representable. So it is the definition is applicable to any functors of an arbitrary category to the category of sets, and sometimes f is, well, may I use symbolically and terminologically, sometimes f is isomorphic to well, I write it like this: f on an object x is isomorphic to x to a. So a is not assumed small here, but it is just a convenient notation for the set of morphisms from a to x. And usually a longer notation is used like this. And we'll call this the power-like functions. Power-like functors. And sometimes f of x is equivalent to a of x, and we denote it just here the inverse. Of course, well, we should not duplicate it, but just to keep some form from x to a, and sometimes call it the exponential show like. So just a couple of standard examples. For example, well, the simplest class of functors from arbitrary categories to the sets are, sorry, let me say that in both cases, A are called the representing objects. It is not always clear whether they exist or not. So consider some forgetful function, or maybe just one example. So consider the forgetting function functor. We have so that f be a forgetful functor from the category of commutative rings. There are several functors, two abelian groups to the monoids, to the multiplicative monoids, well, maybe some others, but we consider the strongest. Just forget everything to the set. So now considering this object, then thinking what is f of a, we can, without any further detail, understand that here a is an arbitrary commutative ring, and f of a is just this ring with all the structure forgotten. No 0, no 1, no addition, no multiplication. But there is it is a representable functor, because if we consider, let's consider the set of morphism in the category of commutative rings of such a representing object as the ring of polynomials in one variables to a so we see that set theoretically such a morphism is defined by the only question 0 goes to 0, 1 goes to 1, and x can go anywhere. So the image of x defines an arbitrary ring homomorphism like this, and selects a certain element of here. So this forgetting functor turns out to be power-like. I would say that not in a quite obvious way. There are lots of other examples in the literature, and perhaps I recommend to look through some of them. Just because the category theory has a reputation of being senseless, and well, one of the official names of it is abstract nonsense, but I'm trying to show that the most natural, purely categorical constructions, the simplest one and the most basic one, are related to some clear and non-standard mathematics that selects the important objects of certain categories. So perhaps this is enough for the examples. Believe me, there are lots of others, and we'll discuss them. But we are going to turn to the problem of representability of the functors that are in the center of our considerations. That is, in applying Grothendieck topology constructions to classification of objects in certain categories. So the next general topic that we have to discuss needs reminding some notations, so concepts and notations. So let C be essentially small. Now, and as we have agreed, it means that it has a catalog for which we are going to introduce now the notation. I think the absolute values are free here, and they are simple enough. So the absolute value of the category, something like the absolute value of the category, it is the set of classes of its isomorphic object. Let's try the basic example. So if C is the category of finite sets, then module C is, let me write now just the equality sign. You can think why it is possible, the set of natural numbers. Well, and we have introduced another notation. So for an object X of the category C, we try to use square brackets to denote its isomorphism class. Now it belongs to the category absolute value of C. So, for example, well, a small clinch of the notation happens here, because for a finite set C, its isomorphism class is the cardinality of X, of course, being a natural number. The problem is that sometimes in many texts the cardinality of a finite set is also denoted like this, and we are not going to use it. Now, what we are really interested in, and well, I hope to reach some results today. So the cases, we are interested in the cases when the catalog of C, we'll say catalog and denote, it belongs to the C itself. It's not an obvious, it's not so easy to give such examples. Well, the set of isomorphic groups is not a group. The set of classes of finitely generated groups is not a group, and so on. However, our main example, let me repeat it, it was boxed some lectures ago. Main example. Here, the main field is supposed to be algebraically closed, and we consider the fields that extend K and are finitely generated. So, I've mentioned this category as the central one and basically corresponding to the birational geometry over the field K, but we are going to discuss not itself, but its subfield, subcategory, the same as here, and with the additional assumption all the the finitely generated extensions of any field have a finite degree of transcendence, and we consider the part of this category of transcendence degree over K being 1. In other words, this is the category of the functional fields on algebraic curves over K. And here its catalog, perhaps I'm lazy to write everything again. Oh, but I perform a trick. I erase this one, erase the box, and use the obvious assertion saying that the catalog of subcategory is just a subset, so I'm writing here just one character of inclusion. So here we meet the catalog of functional fields of curves, and well, they are it is equivalent as a set of curves understood in the appropriate way, curves over K, we have to discuss it. What does it mean? It needs some foundational material. Oh, sorry, I don't need it. So there is a category of algebraic curves. We don't write the word algebraic because when we mean over K, that means that they are algebraic. So this is this bijection is canonical. The correspondence between an algebraic curve and a field of rational number of it is quite canonical here, and therefore this catalog belongs to the catalog of curves. Sorry, here I'm short of space here, but well, let me write it separately, that the curves, catalog of curves, I just give the name to it perhaps, curves over K. It is the set of moduli of curves over K, and it is a disjoint union of this notation is a bit not standard one, but it is a disjoint union of the true moduli spaces of curves of genus J over K. And now these objects J over K, being catalogs, are at the same time belong to the category, well, equivalent to the initial one, varieties, the category of algebraic varieties over K. There are several choices for this category, and well, we are going to specify it and extend it. One of the main goals of the course is to extend it from being a set to being a Grothendieck topology. But first we need some motivation, and maybe I'll have a time just to start it today. Any examples about what is written on the blackboard now? Well, so I reason everything and discuss a small similar question that may seem a bit artificial. But as you'll see, is related to our main consideration. So now suppose our X, our object, is a compact. We do not have not introduced a special notation for the category of compact spaces, and there is no obvious one for it, just because well, some people assume that they should be Hausdorff and use the word bicompact, some do not. So let's just use a word, a topological space, and then we consider the set of metrics on a metric. So the metric of X. Well, by some artificial tricks, we can make it. We can give an interpretation of it as of a catalog of well, something of some category of well, metric structures on a fixed topological spaces. But for the rest of today's lecture, let's go down to set theoretical world. So this set of metric spaces, may I just say in words what it is. So it is a metric space itself. Metric space. I don't understand why it is not very widely discussed, though I think it's both beautiful and important. So the metric is well, the metric, say, raw between d sub 1. So X is fixed, the set is fixed. We consider all the metrics, d and d prime. We consider all the metrics inducing the fixed topology. So it is defined in an obvious way. It is a maximum of difference over maximum over difference PQ minus d prime over PQ and take the absolute value of it, and for PQ running over X times X. So it's important that X is assumed to be compact, then this maximum is attained. It is a nice exercise to check that this is a metric space. Of course, it is not compact. In fact, it is a cone. Maybe reminded that it is a cone of the real functions on X times X. In a real infinite dimensional space, we do not need to in fact, we have a fixed topology on the cone of it, on this cone. However, I'd like to consider it, at least today, set theoretically. So the general construction is that, well, what is very well defined, just one relation to the category language homeomorphism of any topological space is just the automorphism in the corresponding category, and it acts homeo of X acts on the matrix. in such a way that a homeomorph, say, phi on the metric D, we should measure it. It is a metric and we want to measure the distance between 2 points, and it turns out to be that it should be defined as phi inverse. It is well defined only when phi is invertible. Another nice exercise. You can consider it just as some random example of the set of structures that has the structure close to the initial one, but I have just several minutes to relate it to the central object. Now let's consider the first consider X as a manifold, X a smooth manifold, means of course real manifold. Then the above construction can be restricted to the subset of Riemannian matrix of X. They are, it's a nice exercise to see that they are dense among all the matrix of X. And then there is a group of diffeomorphisms of X. That obviously is a subgroup of homeomorphisms, and it acts on the set of Riemannian matrix like this. So may I erase all these rather obvious constructions, and then in the case of Riemannian metric, introduce a new one. So on the there is another equivalence. There is some equivalence on the set of Riemannian metrics. That is the conformal equivalence, or in other words, there is another group C infinity of here is the group of smooth functions, additive smooth function of X, and it also acts on the set of Riemann structure of X in such a way. Here I have a problem how to denote it. Everybody would denote it like this, but I don't like the imprecise, though traditional notations. So let's suppose first we have a phi from here, and it is applied to the scalar. What is a Riemann product? Is we can denote it just like this. This means the set of symmetric products on the tangent spaces. So by definition, it is preserving the angles and using the exponent of y. So now I have just 0 minutes to suggest an exercise. I don't know how serious it is. First, check that there is such a group. Well, maybe in the case when X is a surface of genus J, then we take the set of its Riemannian matrix. You can consider it as an infinite dimensional Banach manifold or something like that, but my suggestion is to consider it purely self-theoretically. And we have defined the action of two groups on this set that can be packed into the action of one group. Since the group of functions on X is being acted upon in the obvious way by the group of diffeomorphisms of X. Only here we consider not all the diffeomorphisms, but just a half of this group of this surface is orientable, and I stress the word orientable as opposed to oriented. We don't need to choose one of two orientation. However, the diffeomorphisms preserving an orientation are well defined. So we put a plus here. So in other words, we consider Riemannian metric up to the scalar modifying it, or in other words, we consider the conformal classes of Riemannian metrics, and up to diffeomorphism. Well, it is suggested to check that this action is well defined, and the result is, in fact, the set of classes of conformal metrics on a surface of genus J. And this class of conformal metrics, by some analytical theorems, said theoretically, is exactly the same as the class of complex structures on the curves of genus J. So again, I have not completed what I planned for today. Now, any questions, comments, or whatsoever? Okay then, now some information. Perhaps it means nothing for the distant participants and means something for those who are present here. I hope to spend 2 weeks and a bit in Great Britain, so hopefully the 2 nearest lectures are going to take place, but be distant, be online. So perhaps for the most of the distant listeners it means nothing. As for the present, we'll discuss now. Okay? Then, thank you, distant people, for your attention.